So let's talk about data. I'm Salvador Gesan.
And I'm Vanessa Cave, and today we're going to talk about experimental design. So, Salvador, what, in your opinion, are the three fundamentals of experimental design?
So, that's a cheeky question because I think most
Cheeky.
people would know those. Um, so we talk about replication, randomization, blocking or control. Um, Obviously, there's many other little bit of elements on this design of experiments, but I was thinking we could talk about blocking first and or replication. Yeah, replication. So, what do you normally use for blocking, Vanessa,
What do I normally use?
when you do your analysis for your clients or for people you work with?
Okay, so a lot of the stuff I do is from designed experiments. So one of the first phases is thinking about your experimental units and grouping them into homogeneous groups and then randomly allocating the treatments. So in the type of work I do, a lot of it's animal trials. So you might block, for instance, by animals which are the same breed and age, or another common one is animals in the same herd or mob.
Uh-huh.
Yeah. And
I
how
know.
about you with plant breeding trials?
Well, with plant breeding trials, we usually define homogeneous units in the field. So it's a physical unit. It's a bit arbitrary, but we define a rectangle or a square or an area, sometimes left or right side. Um, in aquaculture, we usually use pens. A specific pen might represent an unit or a geographical area sometimes. And then in the lab, sometimes you have just, again, arbitrary sections that you define. If you have, let's say, lots of Petri dishes, we define a set on one table or on one portion of the table. But we also have lots of other blocking effects, like,
Mm.
for example, some things like in field trials, they cannot be established on the same day. So we say day might be a blocking because maybe it's too dry one day. We do the same thing with studies in the lab, like with insects. Sometimes we block in the morning because the insects behave in one way that in the afternoon. You probably have heard about batches of chemicals that they are prepared to do a study, and sometimes the preparation of the batches, the blocking, and so on. So there is a lot of things.
Yeah,
And
there is.
yeah, and one of the things is that you probably do too, is just tending to think about what element could create some variability,
Mm.
but it's not necessarily the main objective of the study, which usually is not. I don't care about the difference between morning and afternoon in the insects, but I
Yeah.
care about knowing that there will be a common behavior on the insects in the morning and a common behavior on the insects in the
Yes.
afternoon.
Yes. Yeah. Yeah. Yeah.
So,
That's,
so I usually think about, I don't know you, but I usually think about like we use kind of like the statistical definition that it has to be a unit that is homogeneous.
yeah.
However, it's impossible to be very homogeneous,
Mm.
but at least more homogeneous than you will think because there's something affecting it.
Yes. Yes. Indeed. Yeah. Yeah. Mm.
So one thing I always think about replication, if replication, I should say blocking,
Mm.
is if the blocks are too big to make sense on this homogeneity. And this is something we have a lot on field trials, trees or
Mm.
plants. So, for example, it's not uncommon for breeding trials in trees that we have something like 400 or 600 treatments. And then that means we have 600 plots to establish in a block. which might be half a hectare or a full hectare, which we no longer have something that is homogeneous.
Mm, mm,
So
absolutely, yeah.
I know I'm giving the answer, but that's where we tend to use some more complicated blocking, such as, do you know any of those, Vanessa?
So it's you're talking about some type of spatial design, row column designs, or some other, I guess, simpler spatial designs that you could implement, like ladder
Yes,
squares and all sorts. Yeah, yeah.
that's where blocking becomes a bit more exciting. So you
It
mentioned
does,
about row
yes.
column designs,
Yeah.
where we make a smaller units. Obviously, the most typical one is the incomplete block designs,
Yeah.
or alpha lattice. Sometimes they use the word alpha lattice for a class of them, where we just have smaller units within the block.
Yes,
And
yes.
then we expect them to be more homogeneous,
Yeah.
but then again, they only have a sample of the treatments, because
So
obviously they're going
so
to
it's
be
an
much smaller.
incomplete, yeah, an incomplete kind of blocking designs. Yeah.
And given that you mentioned the spatial, there is also design of experiments that consider some
Mm.
spatial variability. If you know the spatial variability, if you don't know it, you can still optimize the design by separating the treatments in a way that they're not too close together and trying to sample the whole field.
Yes,
So
yes. Yeah, absolutely. Yeah. I was reading up on some of the stuff that Spike Design implements in terms of its kind of spatial designs. And a lot of that's is about based on separation between treatments, the minimum treatment span, and was it neighbor? I can't remember now. Neighborhood distribution.
but
So
yeah,
that's not quite right, but yeah, yeah.
yeah. So um, it is not a form of blocking, but it's a
No.
way to randomize. So now we're touching on the place of randomization,
Yes.
but this is kind of like an assisted randomization, no?
Yeah. Yes.
Um, so I always think about this example where you have, let's say, two blocks together next to each other. They have, let's say, 50 treatments each of them, and then this is physical on a field, and then you
Mm.
have the same treatment, let's say 12, on one side of the one block, and then say the treatment on the other block right next to it, but in a
Yes.
different block. So in terms of data, they're in different blocks and they're going to have different block effects. But physically, they're very close together to each other. That means they might share some microsite,
Mm.
which means they're also sharing the same uh, uh, positive or negative residual. Is going to be highly correlated because they're very close together, and if there's a special correlation on the field. So then in that case, that treatment will tend to be biased upwardly or
Yes.
downwardly.
Yeah.
And that's where you can push them out to be farther away by using some form of a spatial arrangement,
Yeah. Yeah.
considering that, like you said, the neighbors, the neighborhoods,
Yes. Yeah. Yeah.
and so on. So
Thing that I can't quite remember the terminology of. It's
that
unfortunate.
is That is an interesting topic, because in plant breeding, there's been a lot of applications lately on spatial design,
Mm.
especially when you don't have too many replications.
Yes.
But then that also touches on the edge of, you can do the design, but you can also, which is something we won't talk now, but modify the analysis, the linear model or the linear mix model, to consider those issues.
Yeah. Absolutely. Yeah.
So, but anyway, yeah.
Mm.
So I like to think about sometimes lots of layers of blocking when you think about
Mm.
an experiment. And
Yes.
for example, and I'm going to touch on a different topic, but for example, I have um, a field blocking, let's say I have 6 blocks in the field for different treatments, but then you have the person measuring and they cannot do
Mm.
everything on the same day. So let's say you have 6 blocks, but you can only do 3 blocks a day. So that means now you have a second blocking factor.
Yeah.
And then the samples go to they go to the lab, and they cannot be analyzed on the same day. And let's say they had to be processed by, I don't know, like measure some
Mm.
protein content or something. They have to be processed over several weeks and
Yes.
probably in slightly different labs or different
Yeah.
machines. So now I have
Exactly.
like 3 layers of blocking
Yeah.
in there. I probably only designed for the first one,
Mm.
which is just the experimental design in the field, but the other ones are important too. And this is where sometimes, and you probably will hear it, I don't know, it's you have to decide the second blocking, and sometimes you do it orthogonal to the first blocking,
Mm.
or you confound completely with the first blocking.
Yes. Yes. Yes.
And what
Yeah.
is your take on that?
Well, in practice, um, I'm often confounding with another level of blocking because the the original experimental design blocking is just there to reduce the random variation. I'm not really interested in those blocking effects per se. So, for example, if I had 6 blocks and I could record data from half of the experiment, I would one day, and half the experiment on another day. I'd record 3 blocks on one day and 3 blocks on the next. So I'm confounding the day with my blocks because I'm assuming, of course, that I'm not interested in the day effect and I'm not interested in any blocking effects, which um, the the majority of times I'm not. So when would you do some orthogonal blocking? What would be an application of that?
Well, let's say um, I'm using in the lab to eliminate to measure
Mm.
the protein content, and I have 2 machines that do it.
Yeah.
And I'm very sure the machines will give me, let's say they have slightly different scales or slightly different precisions.
Mhm.
So in that case, I will probably think about making that use of the machine orthogonal to some other blocking factor that I don't want to get confused with.
Okay. Yeah.
So in this case, for example, I might, so we have the 6 reps. I might use 3 reps or one and 3 reps for the other, or I don't know. I mean, there's different ways to design this, and actually you can even design it at the beginning of the experiment
Yeah.
with a second blocking factor before they go to the field, so you know which sample will be assigned to which
Yeah.
other treatment.
Yes. In
So,
the ideal situation, I think you would have it all designed before you start your experiment. Um, both
and
the kind of
and it's
experimental
funny,
layout and the secondary blocking.
and it changes from a randomized complete block design to a Latin square or row
Yes.
column design,
Yeah.
because now you have a second blocking factor.
Yeah. Mm.
So so yeah, so
Yeah.
that's one of the cases. But again, it's pretty much what you're saying. There is some interest that there's some interest on looking at what happens
Mm.
with these 2 machines.
Yeah.
Maybe from the modeling point of view, because maybe later I want to have different, let's say, error variances by
Mm.
machine, and I need to identify that. Or just for, oh, are these two different, significantly different? And that should be a concern for the future of the
Mm.
study and repeating the study. So yeah, so
Yeah.
that's an interesting thing. But I do tend to think a lot that when we have several blockings, it's not bad that things are confounded because it
Mm.
makes it easier. Like you said, you can say, I'm going to harvest by block and on different days or in groups of days, and then you have to confound the effect of day with the effect of block or machine with effect. So that's okay as long as you know it. that you
Yes,
can
yes.
separate them. It's fine. It's just going to be an inflated component
Yeah.
because it's summing several effects.
Exactly, yes, yeah. And
But this, go ahead.
and from a practical experience when working with scientists and field technicians, lab technicians, it's to have it, these additional kind of say day of measurement effects or observer effects compounded with the block, it makes it easier to make sure that things are
Operational.
done right. I have unfortunately counted a few times where people have a beautiful designed experiment, say with several blocks and a few treatments, and when they come to record the data, they will record all of treatment A first by one observer and maybe all of treatment B by another observer. And now you've got a real issue because you can't disentangle your treatment effects, which is the one you're interested in, from observer effects. So it's kind of a simple message to give to make sure that the same observer records on the same block. It's all done at the same time. And yeah, so the only thing that differs between the experimental units within the block is hopefully the treatment. Yeah, I mean, there will be, of course, another random variation, but you're trying to control for as many differences as you can. Yeah.
So you just mentioned a case of confounding the blocking effect with the treatment,
Yes, yes.
and then that kind of destroys the experiment.
It does, and that is can be done unwittingly, intentionally. But yeah.
Now, there's another thing I want to bring up about blocking and blocking and blocking when you do the experiment,
Yeah.
which is about the cost in terms of randomization, because you are restricting how units have to be arranged. So if I have 15 treatments on the left and on the right, if I don't have blocks, well, treatment 2 could go anywhere, treatment 3 could go anywhere.
Yeah.
But if I have blocking, I'm saying, no, treatment 2, you have to go on the left and the other copy has to go on to the right. And the cost of that is the degrees of freedom.
It is indeed. But you often benefit from the fact that you're controlling for random variation. So it kind of
So you're bringing the thing is in the sense that I have less degrees of freedom in
yeah,
my denominator because I have a blocking effect on my design,
yeah,
but I will hope to have much less error variance
yes,
because
yes,
the block effect or the noise associated with the block is being extracted.
yes,
And I think that's very nice. And it's a different way to look at degrees of freedom in the sense of looking at them as a restrictions imposed into your design. And this brings the other question is when you do the analysis, do you drop the blocking term that is not significant?
So I have very strong opinions on this, and that
That's
is
fine.
no, you never drop your design factors which are associated with the randomization and allocation of treatments, because then you do get the wrong degrees of freedom. It was designed that way, so that's what should be in your model. And also from just more of a philosophical kind of point of
Yes.
view as well, by testing whether something's significant and saying, oh, it's I don't have this significant effect, then deciding I'm going to drop it because of that. And in essence, you're accepting your null hypothesis, which I never think is a good idea. So again, I wouldn't drop a blocking variable based on a test of its significance. I actually wouldn't ever drop it. Yeah, and you? What's your thoughts,
I
Salvador?
also have the same opinion as you. You put the blocking or one-way or two-way blocking or whatever, and you are married to it.
Yes, yes,
You
yeah, yeah,
stick to it
yeah,
because you restricted randomization, and then you still need to consider that restriction. The way I like to think about it is, let's say blocking is not significant and I get my degrees of freedom back, but that means my error variance, because it's going to be the sum of the square of the errors divided by n minus the degrees of freedom. Well, now the denominator is going to be larger, which means my error variance is going to be smaller.
Yeah.
But wait a second, that error variance is originally represented at the sign with blocking, not at the sign without blocking. And because you already had the restrictions, you lost that.
Yes, exactly.
So,
yeah.
You are listening to Let's Talk Data, brought to you by VSN, a world leader in the advancement of big data software solutions for the agriculture and bioscience sector. Let's Talk Data.
It'd be quite nice now to talk a little bit about randomization. This is a bit topical for me today because I was just been reviewing a paper, and it was an animal trial, and they had 2 treatments, and it was going to just be run on one farm and on one herd. So yeah. So what they did is they brought the herd into the yard, and they mixed them, and they opened the gate, and the first 20 that went through the gate they assigned to treatment A, and then they mixed it again. The next 20 they assigned to treatment A again, and they kept doing that until they had 100 assigned to treatment A, and the remainder were assigned to treatment B. Now, what do you reckon about that, Salvador? Is that randomization?
well, in the limit, probably the randomizations will be okay. I mean, if you repeat the experiment 100 of times, you will get everything balanced. So your concern is that the herds are not well spread between treatment A and treatment B, no?
No, my concern is that how they decided which ones were allocated to treatment A were the animals that went through the gate first. And we know that, and I mean, there's I think, well, we do know that there is differences in kind of personalities of animals. Some are more
Yes.
adventurous than others. There also maybe a difference in kind of age compared to when they go through first. The younger ones might want to hang back with their buddies and all sorts.
And
Yeah.
then they did all the ones for treatment A at the beginning, and then
Yeah.
all the treatment B at the end.
At the
So
end, yeah.
again, we're talking about confounding,
Yes,
because the
I am.
randomization is not being done in an optimal way.
No. Well, I would argue it's not randomized at all in a way.
Yeah,
There's
unless you think that is not going to affect, the way they come out is not going to affect
yeah.
anything on your treat. But I still think it's not very good to have treatment A assigned to all the first few individuals.
Yeah, no.
I mean, I think statistically, if there's no effect of who comes first, who comes last, you shouldn't worry about your experiment. But you're not sure about that.
Yes, the difficulty is we can never be 100% sure of that. We could always and everyone could come up with the reason why it might not be the case.
Exactly.
Yeah, so we've got Now, just by chance, if they randomized it, the first lot to treatment A may have been the ones that would have gone through the gate first anyway, but they actually haven't.
But my concern is you don't know what might affect. Why take the risk to not randomize when you jeopardize the study with such a simple solution as, say, throw a coin and the first one is going to be A or B, the second one is going to be A or B, and so on.
Yeah,
and then you say, okay, whatever it happens is now being randomized, and you don't have much of a concern.
Exactly.
I
Yeah, no,
totally agree with you.
yeah, yes, yeah.
I totally agree with you,
Yeah.
and it's a bit it's important in that sense to think about the implications on the randomization. And we
Yeah.
talked about before about what things are practical or things that are not practical. Because, for example, sometimes you have a chemical that you're applying that you have to do all your replications together. Let's say, think about like a paint. You are going to paint some pieces of block to treat something, but you don't want to do it too late because then the paint will be too dry to paint. So you
Yes,
might end
yes.
up doing, let's say, color red first, and then you do color blue.
Yeah.
But so so then you do color blue later, and then it's going to be incorrect because of that lack of randomization. So you have to come up with clever ways to do it in a randomized way, even if it's in batches.
Yeah, absolutely. Yeah, yeah, yeah. So yeah, the whole point of randomization is to make the comparisons as fair as possible and to reduce, the risk of bias, which is
And this is one of the things that also I like to think like we tend to think a completely randomized design is not very efficient because of the lack of blocking. Think about a field experiment. But on the long term, if everything is randomized, it's an efficient experiment.
yes, yeah,
But,
yeah.
it's the estimation of the error variance is going to be okay. It's going to be contaminated or maybe some potential blocking, but statistically it's going to be correct. Your p-values are going to be correct. Everything is going to be valid in terms of all your statistical inference.
Yeah.
It's just not the best design you can
Yeah,
get.
yeah,
But as long as you respect the randomization, it's still all okay. So, do you have other cases where there's issues with the randomization? So you remember?
yeah, it does crop up quite a lot. Often because some type of convenient sampling's been done. I'm trying to think of a good example, but one it's escaping me at the moment.
I do tend to have, like in some of the studies I have helped with insects. I tend to have, for example, different time of the day. So there has to be a sequence of treatments that are being applied in certain order.
Oh yes,
And
yeah.
that destroys the randomization on the way you think about it. So let's say you apply drug A, then you apply drug B, and then you see the result. And then you say, why don't I do drug B first and then drug A and see the result? And that's because not the way it works.
Okay.
So in that case, which I also think is interesting, you have to think about the combination of A, B as the treatment.
Yes, you do. Yes.
Not
Yeah.
A and B as the
Yeah.
treatment. And that also
Yeah.
means you change in your data. You have to
Yeah.
change your factors because it's a different factor now that you're evaluating.
Yeah. It's a program
So,
of treatment comprising of A and B rather than the individual treatments themselves. Yeah. Ah, that's interesting.
yes, that
Yeah.
happens sometimes.
Yeah.
And so randomization is always going to be critical to validate all the statistical studies. And I'm going to mention one that might create a conflict with an audience.
Okay.
And this
Excellent.
is the high throughput genotyping. Have you heard about those studies where they have the plants in a conveyor belt?
Oh yes, I have. Yes. Yeah. Yeah.
And then first comes the first plant, and they measure everything, and then the second plant, and then they measure everything, and so on. And then when the plants are you see, in this case, the plants go back into back into the greenhouse, or they're constantly moving. So
Yeah.
they're not in the same specific spot.
Yeah.
Because of this constant movement, and
Mm.
so it tends to sound to me a bit like there is no potential blocking or no potential randomization in this case. But I'm probably wrong in the sense that the plants are not being measured all the time. Anyway,
Yeah.
it's just this
Yeah.
concept about moving the plants.
Yeah, that's very interesting. I guess you still can randomize the initial order of the plants on the conveyor belt, particularly if there's kind of you're interested in different cultivars or lines, and you've got some replication.
Yes.
You might be wanting to randomize that by the order of the plants. Yes.
Okay, let's talk about the third concept, which is
Replication.
replication.
So this is one of
Um,
my favorites.
I think it's one of the favorites. I should say favorites, and the ones that makes ourselves a bit more angry when we don't see it and when we see it improperly.
Yes,
So it's in theory a statistical book, and it will say the replication is required in order to have again an estimation of the error variance. Because now we are allowing a same treatment to be on different places under different conditions, evaluated several times. So the variability associated with that treatment will be the error variance or the noise, the background noise. But you need replication of that treatment in order to isolate the treatment from the error and so on.
Yes, yeah.
And we have a lot of topics about how many replications is good enough and so on. So why, my question to you will be, how often you see issues with the replication and the analysis you do?
Well, unfortunately, it's something that crops up quite regularly, particularly pseudo-replication. And sometimes this happens because the design parameters aren't incorporated into the analysis correctly. For example, if animals are in herds and the treatment has been applied at the herd level and herd isn't used as a blocking structure, then you've got pseudo-replication because you're treating the cows within a herd as independent. So that can be a issue that that crops up. Unless that one's resolvable because you can just analyze the data correctly and everyone's happy. The other one is where there's pseudo-replication occurs, or lack of replication, because of an issue in the original design. Issues I've come across a lot is particularly in ecological studies where they have a treatment site. They might be applying, for instance, a new weed control treatment there, and they may have a control site, and lots of information is collected within these sites. So you have a lot of data points, but ultimately you just have one treatment site and one control site, so it's not replicated. And we can do analyses to compare the sites, but the difficulty is we can't generalize our results to saying it's because of the treatment. The sites may be different. We hope it's due to the treatment, but because we don't have any replication, we've actually got no way of saying that. So that's one that comes across a lot.
So that's a good point that you bring, which is replication occurs depending on the experiment at different levels.
Yes.
So you're saying we tend to think about replication at the lowest level. Do I have enough plants from this
Yeah.
genotype.
Mm.
Yes, you do have enough plants, they have a decent replication, but then the question is, do you have
Yeah.
enough sites where you're evaluating this, which is
Yes.
another level of
Another.
replication. And so I agree with you. I mean, we
Yeah.
sometimes forget to think about the other level,
Yes.
which is of interest. And again, this is where I like to study like split plot designs,
Yeah.
because that's where often you see the experimental error for the larger unit, which is the whole plot,
Mm.
which is different replication than the replication you have for the subplot. And if you manage to understand those concepts, it's a little bit easier to see what's going on in
Yeah.
another analysis.
Yeah.
And I'm going to bring another type of pseudo replication,
Oh, yes.
which I have encountered a few times, which is the temporal or repeated measure
Whoa.
replication.
This is a
So
nice one.
once, yeah, once a long time ago, somebody came to me and they did an experiment where they measured some biomass in 7 treatments. And the 7 treatments were done in tanks, and then they were measured something like 10 times over time, the biomass. They were extracting the biomass over different time points. So the student who came to me said, oh, I have 10 measurements for these 7 treatments. And then I asked him or her, I can't remember, how many tanks do you have per treatment? And they only had 1 tank per treatment. So in that case, it's 1 experimental unit per treatment,
Yeah.
measured several times.
Yes.
So,
yeah. Yeah.
and the student was very sad because that gives you 0 degrees of freedom to compare things, even though you think you have lots of replications.
Yes. Yeah. But you don't. Yeah. And another, it's a common example of the time setter replication is when people want to study the effect of, say, a treatment over time, say over week 1, week 2, week 3, week 4. But they run the treatment, the experiment at one point in time. So week 1 is a particular week 1. And then it's whether or not you can generalize that to if you run the experiment starting at a different starting point, a different time, which week 1 would be a different week if you get what I mean. Yeah. So week 1 isn't the first week 1, week 2, week 3 aren't all independently replicated because it's just
Because you
one
have different
week.
conditions.
Yeah. Yeah.
One thing I just want to bring back from the replication is its importance in terms of statistical power in order to test your hypothesis that you want to evaluate. And I think this goes beyond the design of experiments in the sense of how do I arrange the units. It's about saying, if you do this experiment, do you have enough replications to find what you want to find? And I like to bring the case of a student that is doing a dissertation, an experiment for their dissertation. And if they have very poor replication, you will have low power, so you're very likely to not find the hypothesis significant when do you want to compare. And I think that's very sad, because then that means all this work is wasted, because statistically it will not provide reasonable information, even that the information might still be there. So, it's a bit like the treatments are very different, clearly to the eye are different, but with 2 replications per treatment, you don't have the validity. And I tend to think that it's also, again, a bit like what we're saying. If you don't randomize, why not randomize if it helps us on insurance? Why not make sure you have enough replication, so it's also an insurance that you will get what you want to get once you do the analysis.
Yes.
But anyway.
So that's a very good point, and something that's come across a lot when I'm with animal trials, and the same thing you imagine
Human
with
trials
trials on
too.
humans when there's real ethical concerns. So you want to make sure that you've got a large enough sample that you're going to get useful information out of your trial, but you've got to, on the flip side, you don't want to have an excessively large sample so that you're in effect kind of wasting animals, exposing them to experimental conditions that they don't need to be. Because we could get information.
And besides that, it's expensive. So also
Yes, you're right. Yes,
an excessive number of replications,
yes,
just because you can't have an excessive number of replications, because it means a lot more work. But yes, I mean, there's lots of more details on all three of the elements,
yes,
and obviously we only touch a few of the bits, but I think it's important to keep them in mind when we design experiments.
Absolutely.
Well, we should wrap up here.
Yes,
nice
we
to see
should.
you, Vanessa.
You too, and I look forward to talking to you again in our next podcast.
You have been listening to
Let's Talk Data. I'm Vanessa Cade.
I'm Salvador Gessen.